we now know all about strong acids. For example, hydrochloric acid in an aqueous solution. It's strong because it dissociates completely into hydrogen ions or hydronium molecules, depending how you want to view it. And chloride anions. And it's an acid in the Arrhenius definition because, well, once again, this is in an aqueous solution. In the Arrhenius definition, because it is increasing the hydrogen concentration in the water. It's an acid in the Bronsted-Lowry definition because it's donating. This thing is donating these hydrogen protons. And it's a Lewis acid because you can kind of view this hydrochloric acid. It's by giving away this, it's taking these. The chloride is, you can kind of say, it's taking the electrons for itself. So it's an electron acceptor. So that's another reason why it's a Lewis acid. But in every case, it completely dissociates. So it's a strong acid. Now, that by implication, when I call this a strong acid, that must mean that there must be things called weak acids. Weak acids, and you could probably guess what they do. They don't dissociate completely. So let's say you have hydrofluoric acid. Hydrofluoric acid in an aqueous solution. It does dissociate somewhat, so you are going to have some hydrogen break off of the fluorine molecule, so a hydrogen ion, and that's of course in an aqueous solution. No, I was doing aqueous in blue. Aqueous solution, and then that's going to dissociate with the fluoride, the fluorine cation. But this is a weak acid, so it's not just in one direction. It actually goes in both. So you can do, this is an equilibrium reaction, and we know all about these now. Which means that some of this goes in that direction, some of that goes in that direction, and both of these species exist in the molecule. And just as an aside, you might wonder, hey, aren't fluorine and chlorine, they're both halogens. Why is this a weak acid while this is a strong one? And this is just an aside. This is something I always used to wonder about. So if you take a hydrogen, so in general, hydrogen likes to form bonds. Hydrogen, remember, alkali metals, we included everything below hydrogen, right? We included all of these guys. All of these guys, they have this one extra electron in their outer valence shell, so they just want to give it up. And they tend to be very willing to give it up to these guys. So if you have any of these period 2 and below with a halogen, you normally form this ionic salt where this guy gives away an electron, and one of these guys take it, and you have an ionic compound. Hydrogen's a little different. Hydrogen does have exactly one electron in its outermost shell. It just has one shell. But the first shell is interesting because it's complete when it only has 2 electrons. These guys wouldn't have been happy. If you gave 1 electron to these guys, they need to get to 8, so they're not happy. But if you give 1 electron to hydrogen, hydrogen is pretty happy. So when hydrogen forms bonds with these guys here, it doesn't just completely give up the electron. When hydrogen forms bonds with our halogens over here, it doesn't completely give up the electron because hydrogen says, hey, if you give me some of the electron, then I get to 2, and then if you share the electron, you get to 8. So it does definitely like to bond with these guys, but doesn't give it completely up. Now, hydrochloric acid, hydrobromic acid, and hydroiodic, I think I'm saying it right, these are all strong acids when hydrogen bonds with any of these guys, which means it dissociates completely in water. But when hydrogen bonds with fluorine, it doesn't dissociate completely in water. And it turns out the reason why is fluorine is even more electronegative. So this bond between hydrogen and fluorine, so if you compare hydrogen fluorine or hydrofluoric acid to hydrogen chloride, hydrogen fluoride to hydrogen chloride, this bond is much stronger. Not much stronger. I mean, you can measure kind of the energy of the bond, and we'll do that eventually. But this is a stronger bond than this right here. And hydrobromic is even weaker. So hydrobromic, let me draw it. So this one is a little bit weaker than that one. And then hydrobromic, I'll draw it as just one line right there. It's like that. So these are easier to break. So when you put this in water, hydrogen sees these water molecules that have these extra that have these extra electron pairs floating around, and it hogged electrons from here, so it has a partial negative charge. It's tempting for it to disassociate with the water molecules. Well, in this case, yeah, it's tempting, but it still likes to be hanging around. I mean, oxygen is very electronegative, but so is fluorine. So it likes to hang around with both. So it kind of doesn't completely disassociate. So that's why this one is a hydrofluoric acid, is a weak acid, while all of the other halogenic acids are strong. Well, with that said, the point of this isn't to just, look at the periodic table. Let's figure out what the pH is when I dissolve. Let's say I have 1.5 molar of hydrofluoric acid. And by the definition, since I've given this as molarity, I have it in some solution. And in this case, I have it in an aqueous solution. Now, you could look it up, but, well, actually, I'll just write it. So, every equilibrium reaction has some equilibrium constant. So we could write, so the equilibrium constant for this reaction, I'll do it in green. So the constant, and well, since this is an acidic reaction, we'll say it's the equilibrium constant of this, or an acid constant, however you want to say it, for hydrogen fluorine, hydrofluoric acid. Hydrofluoric acid is equal to, well, the products, so it's the concentration of your hydrogen ions times your concentration of your fluorine ions divided by your concentration of your hydrogen fluoride, or hydrofluoric acid, so HFl. And if you look this up at 25 degrees Celsius at roughly room temperature, I believe that is, but let's say it is, you get a constant value here of 7 times 10 to the minus 4th. So, if I have 1.5 molar of hydrofluoric acid, can I figure out what the pH is? Remember, I want to solve for this right here. If I solve for this, and then I know the hydrogen concentration, and then if I take the negative log of that, then I know its pH. So let's see if we can do that. So, I'm throwing 1.5 molar onto this side of the equation, right? But some of it's going to go and form that stuff, right? So let's say X molar gets disassociated. So on this side, let me see if I can do this. So if I'm throwing 1.5 molar on this side, some of it, let's say X molar goes to that side, right? And so let's say, if I have 1.5 molar on this side, once I'm in equilibrium, X goes to that side of the equation, or X reacts to form this stuff right here, disassociates. So once I'm in equilibrium, I'll have my concentration of hydrogen fluoride will be 1.5 molar minus X. And what's my concentration of hydrogen? Well, if X molar or X moles of this, the way you can view disassociate, then we have X moles or X molar of that. And we'll also have X molar of that, right? What if one of these disassociates, then you get one of that and one of that. So these will be the equilibrium concentrations, and I think you can smell some algebra coming our way. So if these are the equilibrium concentrations, let's see if we can solve for X. So we know what the equilibrium constant is. It's 7 times 10 to the minus 4th. We know that the final equilibrium concentration of our hydrofluoric acid is the original 1.5 molar we put in, minus whatever disassociates into this stuff up here. And since X disassociated this stuff here, I have X molar of hydrogen, and I have X molar of fluoride. And this is just pure algebra now. Let's see if we can solve this. So this is equal to, I'm going to need some space to do this. So we get 7 times 10 to the minus 4. Let's multiply both sides times 1.5 minus X times 1.5 minus X is equal to X times X is equal to X squared. And then if we multiply, 7 times 10 to the minus 4th times 1.7 times 1.5, that's 10.5, right? So we have 10.5 times 10 to the minus 4th, that's that times that, minus 7 times 10 to the minus 4th x is equal to x squared. This looks complicated, but it's just a quadratic equation, and there's many videos on that. So let's just throw all of this stuff onto the right-hand side, because I like having a positive coefficient here. So you get, so if I subtract this from both sides and add this to both sides, I get 0 is equal to x squared plus this, so plus 7 times 10 to the minus 4th x, right? I just add this to both sides, so it shows up on this side of the equation, which is right here, minus this. I'm subtracting this from both sides of the equation, so I get minus 10.5 times 10 to the minus 4. Now this is just a quadratic equation here, and just actually I'll throw you a little, we can solve this quadratic equation. We'll get the answer. In fact, I'm about to solve it. But there is an approximation you can do, because if you look at this quadratic equation, this term here, x squared, dominates this term right here. Even when you have relatively small values of x, it dominates that term. So if chemists look at this and they say, hey, you know what? This term is so much smaller. If this term is so much smaller than what's going on here, in a lot of cases you might be able to just ignore it, and then the problem becomes very simple, because if you ignore this term, it's still a quadratic, but you don't have to use a quadratic equation. Actually, I'll do that on the side right here. I'll just do it in a box, because this isn't the exact answer, but it's going to get us pretty close to the exact answer. So in this, make a nice little box here. I'll make a box. So if we just ignored this term, then we'd have x squared. X squared is equal to this, is equal to minus, you would add this to the other side, so you'd have plus 10.5 times 10 to the minus 4, or x would be equal to the square root of this. X would be equal to what? See, 10.5. Let's see, you have to put the exponent thing here. So exponent 4 minus, all right, and I want to take the square root, so to the 0.5 power is equal to 0.0324. So this is 0.0324. So if we make that simplifying assumption, we've essentially solved for our hydrogen concentration, right? That was x. This is x. So this is 0.0324. And if we want to figure out the pH, we just take the negative log of this. So let's do that. So you take the log of it. If you just press log, that's base 10. So you take the log, and we want the negative of that. So you just say minus 1.489, so about 1.49. So it's a pH of 1.49. But remember, I did that using my little simplifying assumption to not solve the quadratic equation. Now let's solve it, just to kind of confirm in our heads that we get the right answer, because that's actually the right way to get the right answer. So quadratic equation, minus b. So x is going to be equal to, let me do it here, x is equal to minus b. So minus 7 times 10 to the minus 4 plus or minus the square root of b squared. So b squared is 49 times 10 to the minus 8, right? 7 squared, and then 10 to the minus 4 squared. Minus 4 times 2 is minus 8. Minus 4 times a, which is 1, times c. Well, c is a minus sign there. We have this minus sign, so it becomes plus. So 4 times 10.5 times 10 to the negative 4, that's what? That's 42 times 10 to the minus 4th power. All of that over 2a. A is just 1. All of that's over 2. So let's see what we can get in this square root right here. So we have, and notice this is a very small number compared to this. This is really all we should care about with the square root, but let's just do it. So 49 e 8 negative plus, so that's that small number, plus 42 times 10 to the negative, or to the 4 negative, is equal to that So that's this value right here. And now we want to take the square root. So to the 0.5 power is equal to 0.06. So far we get x is equal to, I'll arbitrarily switch colors, minus 7 times 10 to the minus 4 plus or minus 0.0648, all of that over 2. And this is equal to, and just to be clear, we can't, if we subtract it right here, we get a negative number. This is a smaller, this is already negative, so if we subtract it, we get a negative number. So let's just worry about the plus sign, because we can't have a negative concentration. So if we add that to this right there, so we have 0.06, and then we have minus, actually let me make sure that it's the minus is there. So it's minus 7 times 10. Right. I just want to make sure I'm not making a mistake by putting a minus there. No, it looks right. So let's see. So we just do our math. So we take this and we subtract that. So we have, let me make sure. So it's minus, I want to make sure you can see what I'm doing. So we have minus 7e 4 negative is equal to that, and then we have to divide by 2. Divided by 2 is equal to 0.032. So 0.032. And remember, this is our hydrogen concentration. It's also going to be our concentration of course, our fluorine atoms, but we don't care, or ions, we don't care about that. We just want to figure out the pH. So this is 0.032, which is very close to our approximation before. But now we have the exact number. So let's take the log of it, and then take the minus of that. So the log of that, and then you want to put a minus in front of the log. So the exact pH is right there. So our pH of hydrofluoric acid is equal to 1.49. So once again, pretty low pH. But notice, this pH, this is 1.5 molar. This is 1.5 molar of hydrofluoric acid, while 1 molar of hydrochloric acid had even a lower, it was even more acidic. It had a pH of 0. So even though we put more acid here, we didn't get our pH as low as when we used only 1 molar of hydrochloric acid. Anyways.